Okay, so this is February 9th, 2026. And I'm going to share the screen here. And today's subject is a very interesting one. It has a huge effect on the subject of variable frequency drives. So thank you for joining. And for those of you that are new to the class, this is a class that we hold every Monday morning at 7 a.m. and various subjects, everything from sensors to motion control to precision gear drivetrains to variable frequency drives. Today and tomorrow, or today and next week, we're going to be focusing on the harmonic distortion and power factor issues associated with variable frequency drives. That's today. And Monday, we will be focusing on the technologies that the drives industry has been developing to deal with harmonic distortion and power factor in general. Two very interesting subjects, two subjects that heavily affect the ability for people to sell drives, to apply drives, to successfully run variable frequency drives in their plants. Today, we're going to talk about harmonic distortion and power factor, true power factor, which you will see is defined as your distortion power factor plus your displacement power factor. Now, okay, we're going to get in a little weeds here. It's going to get a little deep, but I want you to, I assume you can all see my screen. And this is something that I learned. I'm a mathematician. That's how I was educated. And this is something I learned that helped me in a lot of areas, including the technical aspects of the career that I chose. And the fact is that there are no complex problems. Everything we're talking about today, when you hear about sine waves and Laplace transforms and all these different mathematical issues associated with the subject, just remember, all this stuff breaks down into very, very simple components. And that last statement is very telling for me. The most complex computer programs, which today include AI, are nothing more than an assemblage of ones and zeros, because that's what digital computing is based on. So as you go through this, just try to remember we break down these issues into simple problems, and then we put them back together again and we have understanding. If I'm successful in helping you do this on today's subject, then I've done my job, because today's subject is one of the more complicated issues that we deal with. So, now, I don't know how many of you have had trigonometry in your educational past, where you have sine waves and cosines, and there's a lot of other different waveforms associated with trigonometry. But I want you to understand the basic sine wave. And a sine wave is something that varies, in our case, around electrical zero, and it's an analog waveform. Now, the sine wave has some very simple values. It varies from 0 to 1. The cosine is the exact opposite of the sine. So cosine is C-O-S-I-N-E and sine is S-I-N-E. If we look at sine waves, here are two sine waves. And they are, the red one happens to be voltage, the blue one happens to be I, or current in this application. And by the way, if anybody can tell me why we always refer to amperage as I, that's an interesting little piece of trivia. But you can see that that is a sine wave. The cosine of the red wave would be something like this. It would be the exact opposite. It would go down and up at this point and then go up and down at that point, being the mirror image. Now we don't have to deal with the other trigonometric functions today. We only need to understand basically the sine wave. So I'm going to allow Yaskawa their voice in this presentation because they have some very good videos. This is also a little bit of a selling point for Yaskawa's e-learning curriculum, which I think I had it up here. Let's see. Yeah, there we go. So the e-learning curriculum at Yaskawa is part of the website. You can go there and go to training and click on the, oh, please. Yaskawa doesn't trust me to be a human. And then you can list, all of these classes are part of the e-learning curriculum at Yaskawa. They're all, roughly 15 to 40 minute videos. And things like network communications, which is very important for drives these days. We're going to go to a video. Let's see if I can find that video that I downloaded. Oh, I know where it is. Okay, so I downloaded this video from the e-learning or from the e-learning curriculum. And it happens to be 1.4 gigs. So it took a little bit of time to download. This will give you an idea of the quality of Yaskawa's
training department of
presentation.
Yaskawa America Incorporated presents Harmonics, a guide to understanding and successful control. I'm Steve Kaler, and today we are going to answer these questions. What are harmonics? Why do we care? And when we care, what are we going to do about it? Now, if you're involved with a facility that uses a large amount of electrical power, these are very important questions. And there are lots of good reasons that the answers matter. It's essential to have an understanding of how harmonics work and how to handle their effects. So to begin our understanding, let's get down to the fundamentals. All electrical power is distributed as a sinusoidal voltage. Why a sine wave? Well, it's easier to understand that if you look at the basics of how a generator works. At its simplest, a generator is a rotating magnet in a stationary coil of wire. The rotating magnet, or rotor, is called the field winding. The stationary coil is called the stator winding. The field winding, or rotor, is excited by direct current by means of carbon brushes and slip rings. The field winding is turned at a constant speed by a mechanical power source connected to the shaft. As the field winding turns, the magnetic flux sweeps by the stationary stator windings, which induces voltage in the stator windings. And in a two-pole generator, the induced voltage makes a complete cycle of values for each complete mechanical revolution. And what do you have? A sine wave. In a two-pole generator, the frequency of the induced voltage in cycles per second, or hertz, is the same as the speed of the rotor, or field winding, in revolutions per second. The electrical frequency is synchronized with the mechanical speed, and for that reason, this type of equipment is called a synchronous generator. So, a two-pole synchronous generator turned at 60 revolutions per second, or 3,600 RPM, will produce a 60 Hertz voltage sine wave. Power generation in the world today is a three-phase system. So, synchronous generators used for power generation produce three-phase voltages displaced 120 degrees in time with respect to each other. A simple three-phase, two-pole synchronous generator with one coil per phase is shown right here. When an electrical load is connected to the voltage source, it draws current to perform work. If the current follows in the same sinusoidal pattern as the voltage, then the load is said to linearly follow the voltage and, in short, is called a linear load. However, If the connected load does not follow the sinusoidal wave shape of the voltage, then the load is called a non-linear load. Non-linear loads cause stress on the transformers and generators that make up the power system, also known as the power grid. This stress has been found to be primarily thermal in nature. In other words, stuff gets hot. And even though the load that is doing the work can be very efficient, the overall energy used to perform the work of a non-linear load is much higher than a linear load. Power systems carrying non-linear loads are less efficient. So it's important to find them and take corrective action to reduce their negative impact on the power grid. Now, in the real world, the grid is filled with all types of devices that create nonlinear loads, like power supplies for computers and electronics, lamp dimmers, speed drives. A great many things consume current intermittently in blocks or bursts, causing the sine waves of the power grid to become distorted. Now, if you're an electrical power utility, distorted current waves are a problem. And, as mentioned earlier, distorted waveforms increase line losses. They stress generators, they overheat transformers, and they can destroy power factor capacitors. The other users down the street who share your electrical grid care as well. Distorted current drawn by your nonlinear load can result in distorted voltage on the grid. Distorted voltage can shorten the life of your neighbor's power line equipment and increase the cost of their power. It overheats their transformers, stresses their switchgear, and increases neutral currents. The greener world also cares about distorted current because it wastes energy and it increases heat. There is an important aspect to keep in mind when it comes to distorted voltage on the grid. The distorted current that is drawn by the nonlinear load is local in nature and flows only into the nonlinear load consuming that current. However, when distorted current is transported to the nonlinear load, it causes distorted voltage drops all along the power system, which leads to distorted voltage on the grid. Voltage is common to all users, and distorting this common grid voltage can create widespread losses and may result in faulty operation of many types of electrical equipment. In order to reduce the level of distorted voltage, it is important to limit the flow of distorted current. To get a clearer understanding of why this is so, let's use one of my favorite simple teacher analogies and imagine that voltage and current in the power system are like pressure and water flow in a household or multifamily water system. If you are opening and closing the water system of one area, well, bursts of water are coming out. But bursts of pressure are going in the other direction in the system as well. If the bursts are strong enough, the water system of the guy next door, the one that normally flows so smoothly, won't be so smooth anymore. At least it won't until you stop surging the system on your end. So obviously there needs to be a remedy to distorted waveforms on the power grid. But before we can try to fix power inconsistencies, we really need to define and quantify them. As mentioned earlier, a distorted current waveform creates heat in the power delivery equipment. Resolving a nonlinear waveform into its sinusoidal components is called harmonic analysis. Harmonic analysis will estimate the heating effects due to nonlinear currents flowing through circuit breakers and transformers. And that's where this gentleman, Mr. Fourier, enters the picture. An 18th century mathematician and physicist, Jean-Baptiste Joseph Fourier, introduced the notion that even the most complex waveforms could be understood and mathematically defined as a composite of a fundamental frequency sine wave with other sine waves in multiples of that frequency. We call these waves harmonics. Fourier also gave us a complex mathematical equation to define the relationship, an equation that has struck terror into the hearts of engineering students and physics teachers ever since. Right here is a demo of a wave being resolved back and forth between its fundamental wave and the distorted or composite wave by adding or subtracting some of its harmonics. Now we are looking now at how multiple waves can exist in the same system at the same time. By looking at this graphic, you can see that constructing a composite wave is fairly intuitive. For example, if the fundamental wave says go up 6, while the harmonic says go down 2, the result will be a composite wave that goes up 4. Now, deconstructing a highly distorted composite wave into its fundamental and, say, the 20-some harmonics that distorted it is much less intuitive. And this is the math that makes that possible. The ratio of harmonic content to fundamental is defined as total harmonic distortion, or THD. THD is expressed as a percentage of the fundamental. The higher the percentage, the more distorted the waveform. Now, our primary concern is voltage harmonics, since voltage is what is common to all. We have to understand that the only way to limit voltage harmonics is to minimize current harmonics. If the current harmonics are under control, the voltage harmonics are generally acceptable. Theoretically, there are both even and odd-numbered harmonics. Typically, in an AC power system, even harmonics are absent. Our concern here are the odd harmonics, which are present in an AC system and do contribute to total harmonic distortion. Odd harmonics that are multiples of 3 in a 3-phase power system, called triplet harmonics, theoretically are absent in a balanced 3-phase system. However, perfect balance is rarely the case, and one must be ready to deal with triplet harmonics that form a noticeable amount of losses in an AC power system. Now that we have a measure of harmonics called total harmonic distortion, the next question becomes, how much distortion is too much? Well, the industry standard is IEEE 519-1992.
Okay, I'm going to interrupt here for a second. The current standard, this has been updated. So the current standard is IEEE 519-2014. And we'll have a separate class on that standard and how to comply with it, and especially when you're bidding projects, and using tools like the Yaskawa Harmonics Estimator to ensure that what you're bidding is compliant to the IEEE 519 standard. But I just wanted to point out that the current standard has been updated.
It defines the acceptable levels of TDD, or total demand distortion, at the point where the customer ties into the power grid, called the PCC, or point of common coupling. And note that we have cleverly changed from THD, total harmonic distortion, to TDD, or total demand distortion. Now, what is TDD? And how is it different from THD? Well, TDD, which again stands for total demand distortion, is a moving average of the THD based on the system rated current value, where THD is based on the fundamental current on a cycle-to-cycle basis, which changes with load. TDD uses a much longer averaging time, as long as 15 to 30 minutes, and is based on the rated current of the system. The basic definition of TDD is based on the pure and simple truth that distorted current waveforms result in increased temperature of the power delivery equipment. Hence, a time variable is introduced into the picture. The value of THD on a cycle-by-cycle basis is not meaningful when the main intent is to reduce power loss and reduce heating in the power delivery equipment in an optimal way. The 519 standard calls for measurement at the point of common coupling with the utility, but engineers specify its use at the input terminal of the variable frequency drives. This standard is often too rigorous, but it's so commonly used that it is important to address its abuse. The 519 standard is expressed as a table. An important variable described in the table is the relationship between the size of the power source and the size of the load. This relationship, called the short circuit ratio, is a measure of load current to available current. If you have a very big power source powering a very small load, the 519 standard allows you a large amount of TDD, up to 20%. If you have a small power source with a relatively large load, the standard dictates the need for a lower level of TDD, as low as 5%.
In almost all cases where we're dealing with bid environments or actual analysis of loads in typical industrial facilities, we're going to be dealing with the 5% scenario. The 20% scenario, frankly, I've never seen that.
Here's where the discussion comes around to the world of variable speed drives, also known as variable frequency drives, or VFDs. What kinds of harmonics do variable speed drives create? Well, the answer is it depends, especially based on the input rectifier scheme and the size relationship between the drive and the power source. Fortunately, there are things you can do to reduce current distortion on the power source, and these solutions are commonly much more cost-effective than increasing the power source's size. Mitigation step 1 is to add a DC link inductor, otherwise known as a reactor or choke, in front of the DC bus capacitors of the drive. An inductor is a good way to begin making the waveform more continuous or more sinusoidal. You can use an inductor to reduce your THD to about 40% in certain situations. Mitigation step 2 is to add an input reactor in front of the drive. An input reactor also helps protect the drive from some forms of noise and power disturbances, which is a nice bonus. This adds impedance that can bring levels of THD down to about 35%. Many times, simply adding a DC link choke in combination with either a 1% or 2% impedance input reactor is sufficient to meet TDD levels at the point of common coupling, which typically is the secondary of the main feed transformer. Another method of mitigating harmonics is to use an active filter. In facilities with large drives or many small drives, active filtering techniques can be used to help reduce THD. Active filtering techniques typically are more efficient and can be economical as well. The shunt active filtering technique adds a set of canceling harmonics back into the circuit, which are meant to counteract the harmonics generated by the nonlinear load. Shunt active filtering techniques provide the best performance for the lowest cost. However, shunt active filtering is a systems approach and requires the active filtering equipment provider to work closely with the plant manager, specifying the equipment, location, and size of the unit for installation. Another option to reduce THD is to use a variable speed drive with a 12-pulse input rectifier. This approach takes a 3-phase input and feeds it into a phase-shifting delta-delta-Y transformer. Delta-delta-Y type isolation transformers are readily available from a variety of manufacturers. The theory behind this approach is simple. The harmonics generated by a 3-phase AC to DC rectifier found in many VFDs is given by the formula H equals KQ plus or minus 1. Where H is the harmonic number, Q is the number of humps per electrical cycle on the DC bus, and K is any integer. For a 6-pulse drive, that's 6 humps on the DC bus per cycle, harmonic number H yields values of 5, 7, 11, 13, 17, 19, etc. As you can see, converting a 6-pulse rectifier to a 12-pulse rectifier, that's 12 humps on the DC bus per cycle, harmonic number H yields values of 11, 13, 23, 25, etc. The 5th, 7th, 17th, and 19th harmonics are absent in the 12-pulse rectifier scheme, which results in a low level of current distortion. Now we're getting input current that is beginning to look very sinusoidal and brings us to the level of 9 to 14% THD. This approach adds a modest amount of extra cost due to the additional components of the 12-pulse rectifier plus the transformer. But in an application where a low-voltage VFD is to be connected to a medium-voltage power supply, a step-down transformer will be needed anyway. So a 12-pulse transformer used in a situation like this may not be a major cost adder. Yaskawa offers the 12-pulse input rectifier scheme standard on its A1000 drives. One step above the 12-pulse rectifier scheme is the 18-pulse rectifier scheme. 18-pulse rectifier schemes are typically found in larger horsepower VFDs and, just like the 12-pulse, require a phase-shifting transformer. Using the formula we discussed earlier, H equals KQ plus or minus 1, an 18-pulse rectifier, that's 18 humps on the DC bus per cycle, harmonic number H yields values of 17, 19, 35, 37, etc. The 5th, 7th, 11th, 13th, 23rd, and 25th harmonics are absent in the 18-pulse rectifier scheme, which results in a very low level of current distortion. An 18-pulse rectifier yields a very sine-like wave, 5 to 5.5% THD. The downside of the 18-pulse rectifier approach is that it is usually available only in large-sized drives. A typical 15-horsepower industrial drive isn't available with an 18-pulse rectifier scheme. 6-pulse schemes are most common, and 12-pulse schemes are available in some instances. Large horsepower HVAC drive applications are often held to a very strict conformance of IEEE 519-1992 and may benefit from a VFD with a 12-pulse rectification scheme. The next two configurations are non-standard and can also be effective in some situations for low-cost mitigation of harmonics. It's possible to use a hybrid.
Okay, we're going to stop this presentation here because he's going to get off into the weeds and this is not applicable to the subject at hand. So, I do want to comment on one thing. The passive solutions that were shown here, such as this 18-pulse rectifier scheme, they're passive because this transformer here is a passive device. And quite frankly, we don't use these anymore. I showed this for background on what we used to do prior to the subject of next week, which is active front-end drives to solve the distortion issue. Gives you a little bit of background on what we used to do. The reason this doesn't work anymore is because it never really complied to the IEEE 519 standard in variable load applications. It complied to the letter of the specification, but in actual reality, it didn't work. And this is why. This is a passive device, and therefore it has to be sized for a certain load, which in this case is full load, and therefore has an optimal performance at full load, where it does comply to IEEE 519. However, why are you putting a variable frequency drive on a motor if you're going to have a constant load? You're going to vary it. You're going to vary the speed, which means you're going to come off of the ideal design point of this 18-pulse transformer, and now its performance degrades. So in a typical fan or pump where you're running it at, say, 75% of speed, this isn't compliant anymore. Its distortion is higher than IEEE 519. Remember, though, this came about in the 90s. It was good technology then. It was the best we had. Next week, we will talk about active front-end technologies that basically replace this entire scheme here on the front end of the VFD and react to load because they're active and therefore comply to IEEE 519 down to, say, 20% of load and all the way up to full load. But this is good background. By the way, from a cost standpoint, when you add an 18-pulse transformer onto the front end of a VFD with the associated extra diode bridges, you basically double the cost of the VFD. That's the main reason why it's only done in, say, 100 horse and above. Because down in the smaller horsepower ranges, you don't really need to suppress the harmonics on those small drives as much because they're a smaller percentage of the total load. You can get away with input reactors, etc. This doubles the price of the VFD. How much does an active front-end VFD cost? One that I described earlier as solving the actual problem throughout the load range. Well, it's about equivalent to the cost of an 18 pulse. Now, there's a very interesting historical phenomenon. When a better technology comes along, like the transistor for tubes, like DVDs for cassettes, like radial tires for bias ply tires, they don't take significant market share until the cost of purchase of the superior technology equals the cost of purchase of the inferior technology that it replaces. Check me out. Go Google the history of these things. That is pretty much a consistent rule in history. So while we've had active front-end technology for many, many years, 18 pulse persisted well into this century, even though it was an inferior technology, until economies of scale in manufacturing brought the active front-end stuff that we will describe next week down to roughly the equivalent of an 18 pulse solution. Now, you can picture that because on bid day, when both 18 pulse and active front ends are allowed on the spec, if 18 pulse is cheaper, it wins. Now, cost of ownership on 18 pulse versus active front end, we'll talk about that next week, vastly in the favor of active front end. But that is why 18 pulse has persisted to this day. I still see specifications for 18 pulse. However, some really large organizations that affect our business, LA County Sanitation District, for example, largest wastewater utility in the Southland, basically has eliminated 18 pulse from their specification and only allows active front end, again, which we will describe next week. So, thank you, Yuskawa. When we talk about true power factor, which is the next subject, I promised to talk about distortion, and I promised to talk about true power factor today. True power factor is the sum of, here we go with that math again, there's cosine. This, in the numerator of the fraction, is displacement power factor. This, as you can, if you remember from the previous presentation, is the formula for distortion power factor. Now, true power factor is the product, or is the sum of both. And when we talk about displacement power factor, displacement power factor is this. Note that the voltage sine wave is here, and it's pure, it's not distorted. The current sine wave is here, and it's pure and not distorted. Now, in some cases, the current sine wave may be a higher amplitude than the voltage sine wave. That's not bad, as long as it's sine wave. However, there is an angle of displacement between the start of the voltage and the start of the current sine wave. This is called displacement power factor. And this is what we had to deal with prior to variable frequency drives. When we ran an AC induction motor and we only had a contactor to run it, no variable frequency drives, well, the power company basically said that we want the displacement power factor to be 0. That means that this current waveform needs to line up and start and march in step with the voltage waveform. As an AC induction motor runs at full load, its displacement power factor is pretty good. The current runs pretty tight to the voltage. However, when you offload that motor, load comes down below the rating of the motor itself, the current starts to lag the voltage. And this is what the power companies try to prevent from happening. But we're talking about ancient times here. This is the 80s and 90s. Displacement power factor, as far as a VFD is concerned, is not a concern. The VFD is placed between the motor and the power line and separates the motor electrically from the power line. Basic reason is that this is a VFD circuit here. Here's the motor. Here's the power line. You're basically taking AC, rectifying it to DC, and then inverting it back to AC again for the motor. This section here completely electrically isolates the motor from the line in terms of distortion and displacement power factor. The motor doesn't affect the line power factor because of this DC bus. Basically, we're taking AC and whiting it out to DC and then recreating the AC going back to the motor or going forward to the motor. So, understanding that, then the line here, the power factor of this line is concerned with this. In other words, what it's facing. The displacement power factor of a VFD is so small as to be insignificant in this discussion. However, the distortion power factor is a big deal. So, when we talk about true power factor, sorry, I jumped to the wrong presentation. True power factor is distortion plus displacement power factor. We can basically not concern ourselves with the displacement power factor, and we can focus on the distortion power factor when it comes to VFD applications. Now, these are distorted waveforms. They don't look anywhere like a sine wave. These are displaced waveforms. So let's go and talk about distortion and how we can correct it and how it affects total power factor. Now, total power factor basically is, I don't have a good, no, I don't. Bear with me one second. So total power factor is basically the efficiency with which we use power coming from the line. And why is it important? I'm just going to step out. You can ignore this diagram for a second because I'm going to step out of the technical discussion and give you an idea of why this is so important. I don't think anybody, even the most remotely isolated person in our profession, has not heard about the fact that the Western grid in the United States is in trouble. In fact, the word trauma has been used in association with that condition. The power grid in the United States is not in good shape. It hasn't had the capital investment to upgrade the capacity. We've had a lot of issues in terms of power generation. And at the end of the day, usage has continued to climb in the United States while we haven't kept up with our maintenance and upgrade on the grid. Now we have the need for supplying these data centers, which are projected to double the load on the grid. So what we're using now, 360 million of us, to power our TVs and lights and whatnot in our houses and our industrial plants, that much again is apparently projected for all these new data centers that are going to come out, notwithstanding Elon Musk's attempt to throw them up in space and power them from solar cells directly facing the sun. Now, bottom line is demand increases, the grid grows ever more fragile, the power companies are coming out in various states and creating new rules that vastly affect the financial picture of usage of variable speed drives. And you're seeing this come out in your bid specifications for new products. You're seeing it come out in a demand for existing facilities to upgrade to comply. Why? Because if you don't comply, the power company is going to whack you with a lot of money on your charge bill. It's going to be a power factor penalty. It's going to be increased rates called differentiated rates for people who never have a chance of complying. The PUC, as represented through PG&E, Southern California Edison, San Diego Gas and Electric, and all of the other minor players, are basically announcing that they will come out with these power factor motivators, if you will. I don't know how many of you noticed it because the program was horrible, but the incentive program came out several years ago giving you rebates to install power factor compliant equipment in your plants. The specs were written poorly. It cost more money to comply to the spec than you got back on the rebate, and surprise, surprise, nobody did it. That was the carrot. They don't have a choice. Now they're bringing out the stick. And so in places like Washington, state of Washington, you want to turn on a new plant, somebody comes with a harmonic analyzer, hooks it up to the point of common contact, which, as Steve said in the presentation, is typically the secondary of the main transformer. And they basically want you to run your plant at load, and they will monitor your power factor at the point of common contact. And if you comply, you get your usage permit. Now, a lot of this is done through digital simulation, etc. But if you don't comply, you don't get your usage permit. Now, that's enforcement. One of the issues with power factor specifications is that you read it on the spec, you tried to comply as best as you could on the bid, but nobody was checking. And the guy that cheated was cheaper on the bid and basically won the bid. And did he get his feet held to the fire? In many cases, not. The power company in Washington was one of the first to enforce. And now up there, we have a very good market for power factor compliant variable frequency drives, typically active front end stuff now, as I said, because the 18 pulse drive is basically the bias ply tire compared to the radial tire. In California, that's coming. So that's going to change the financial landscape of all of these bid jobs for new construction using variable frequency drives, whether it's HVAC, whether it's the water utility business, fresh water or wastewater. You know, these markets are huge in California for variable frequency drives. It will also affect the industrial landscape because new plants that are being built are going to have to comply as well. Old plants will be forced to comply because they're going to get dinged with a power factor penalty. Now, the way a power factor penalty works is the same as your peak power penalty. Right now, those of you familiar with an industrial power bill, there's a peak power allowance. And if you go past it for X number of seconds, you get put in the penalty box for 30 days and you pay a higher rate. It's a pretty heavy incentive not to overload the grid more than you've agreed to on your contract with the utility. It's called peak power penalty. Power factor penalty is slated to work the same way. Now, this is somewhat conjectural because they haven't come out with the final rules yet, but they're coming. And when I say they're coming, it's more like in the next year or two, not the next decade. Power factor penalty, you exceed your, well, you fall below your allowable power factor in this case, and you get in the penalty box for X number of days and you pay a higher rate. This financial incentive will change the landscape in terms of how VFDs are specified and sold. The enforcement, as I said earlier, is the key. So why we're talking about today, this is more important than it was back when they didn't really enforce it. So again, the distortion power factor here we have the fundamental waveform. And here we have the waveform that we end up with in terms of the variable frequency drive with no filter, just a diode bridge. It doesn't really look like a sine wave. A lot of distortion. Distortion being the difference between the fundamental of the black and the green, which is the actual waveform. And then through the Fourier transform, we are able to convert this into different sine waves of different frequencies to allow us to do harmonic analysis. Third, fifth, seventh harmonic means if this is a 60 hertz waveform, the third harmonic is 180 hertz. The fifth harmonic is 300 hertz. The seventh harmonic is 420 hertz. The Fourier transform allows us to take this waveform and turn it into all sine waves, albeit higher frequencies than the fundamental, but a multiple of the fundamental. And all this stuff here needs to go. Knowing how these different frequencies lay out on the analysis helps us to determine what equipment we can use to mitigate the yellow, red, and blue stuff. There is a very convenient program that Yaskawa makes because this allows you to forget all this other gobbledygook, and we're going to go through this in a different class. But the Yaskawa Harmonics estimator does all the math for you. It allows you to lay out what your single line diagram looks for the power situation that you're addressing. That means you have to get the single line diagram from the existing plant or from the new facility that you're bidding drives on. That's necessary. You then have to get the transformer data, which is pretty easy to get. It's right off the nameplate of the transformer or from the specification. The spec cannot tell you you have to comply and not give you the necessary information. Well, it can, in which case it's a bad spec. But you get that, you define your system in a single line diagram, which looks something like this, where the program allows you to add in what linear load there is, how many 6-pulse drives, how many 12-pulse, how many 18-pulse, and then how many active front-end drives there are. Again, we're going to be talking about active front-end next week. This tool is available from Yaskawa. It's a free download. Our software is always free. And it is the tool that you can use. All the other tools that you get from ABB, Danfoss, what have you, they all pretty much function the same way. Okay, so that's the Yaskawa Harmonics estimator as a tool. Now, as we're closing in toward the end of this class, we have talked about displacement power factor, which from a simplicity standpoint, we don't need to really deal with, just understand it, but it's not part of our world in drives. And distortion power factor, which is what we cause in the power line. And distortion power factor is caused by current distortion. In other words, a device that pulls current in a nonlinear fashion from the voltage that's supplied, and thus sends back reverberations into the grid that distort the voltage itself. And as Steve said, it's the voltage we're really concerned about. But what we can affect as end users, in our case, engineers and appliers of VFDs, is the current. We correct the current and we correct the voltage distortion. So that's why we're focused on current waveform distortion, so that we do not cause voltage waveform distortion that travels up to everybody else connected to the same grid that we're connected to. Now, we have a tremendous amount of diagrams, okay, to show, but there's one that I really want to focus you on, and that is this one. This particular technology, which is used in 90% of the drives today, is the good old diode front-end, DC bus-based, transistorized VFD. Line, diode bridge, AC to DC. This DC bus here is backed up by a bunch of capacitors. This green thing here represents capacitors. And then this section here is transistorized, and it makes the AC going back to the motor, albeit of the voltage and frequency that we want to control the motor speed. In this type of device, as Steve was describing in his video, we put a bunch of filters on this thing. We're basically band-aiding this, but this is, while it was a great design in 1983 when it came out, it's not a great design today for the problems that we're now facing. It's causing those problems. So a lot of band-aiding going on, putting filters here, increasing the cost. And those filters being passive don't really work that well throughout the entire load range. However, the pulse width modulated drive, to give you an idea of why it causes all this problem, is this is the output of the drive. Now, that's pulse, 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 pulse. Similar to the guy on that hose that was causing pressure variations in his neighbor's bathroom faucet. This sort of pulse, 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 pulse ends up causing this sort of distortion on the general power line to which this pulse width modulated load is connected. Now, as I said, this is a very kind of deep subject, and those of you that are really interested in getting into the nitty-gritty of it, there's a lot of things that I can send you to help you understand this better on a technical level. If you are interested in doing that, you have my email based on the announcement that I send out. Send me a request as to what your specific interest is, and I will supply you with all the data that you can possibly want. For those of us that are less inclined toward the technical but want to understand this subject so that we can operate efficiently from a commercial standpoint, I'm going to summarize in the last few minutes like this. Number one, compliance is coming, and therefore this is a necessary subject to address. You cannot effectively bid and supply variable frequency drives and other power components without compliance to the IEEE 519-2014 specification and therefore to the total power factor. I'm going to step out a second and remind you that for the most part, it's 5% distortion that we're after. But what power factor are we after? And typically, the total power factor, of which distortion is a part, is also going to be a 5% equation. Power factor is measured as perfect being 1.0. 0.95 power factor means you have 5% waste energy. And that's really what the power company is going to want to measure at your point of common contact. So, IEEE 519-2014, 5% current distortion. That's what we're after. That gives us the ability to comply to the total power factor picture, which is greater than 0.95. So back onto the summary, compliance. Non-compliance is going to cost money. That money will drive the investment in more expensive equipment that does comply. Number two, there are tools like the harmonics estimator that allow you to do this without having a mathematics degree that understands who Fourier was. You do need to have certain information. That information is two parts. It's the transformer data of the main transformer, and it's the single line diagram of all the components hooked up to that transformer. You have that. We can help you by training you on the harmonics estimator, and then you can accurately project the distortion and power factor for the system that you're bidding. Finally, the technology has changed such that we don't use passive components anymore. We use active components. We use a new class of variable frequency drives. In some cases, it's a complete departure from this original design. And to give you a little precursor of it, there's a diagram of an 18 pulse transformer. There's the main transformer with its 3 rectifier sections on its output. This is active front end. If you note, this diagram is basically this diagram here. This isn't hooked up anymore. What we've done is we've taken this, flipped it around, and reconnected it here, sort of a copy and paste. So this is the traditional active front end technology. Not exactly new, but it is active and it does comply. And in many cases, that's what the state-of-the-art product is for certain manufacturers. And then what we will talk about next week, in addition to active front end, is we will talk about this. And this is a matrix drive. Note the complete difference in power circuitry of this product versus that product. This is the first major departure in my career, and I've been in drive since 1980. It's been a long wait, to be perfectly frank about it. But the matrix technology is now a player in this market, has been since 2010. But again, remember what I said. The old technology doesn't get replaced by the new, better technology until the purchase price of the new, better technology equals the purchase price of the older, inferior technology. That's just the way it works. So we've been at that point since before COVID. So the active front end technology, whether it's traditional, which is perfectly functional, or whether it's matrix, is growing dramatically. You should see the expansion in our factory to build this drive. We build this drive as well as this drive, as opposed to the existing technologies. And we're talking about 100 horsepower and above here. Major change in the landscape of what we're bidding for these projects. So next week, we will continue on with the actual discussion of active front end technologies. I'll leave you with this thought. We have achieved price parity with the old passive technology, the 18 pulse technologies. Cost of ownership, we were better than them a decade ago. And we'll talk about cost of ownership as well, but it's the cost of purchase that determines what gets purchased. Like it or not, that's just the business facts. Today, we have an active front end technology to address the total power factor compliance and the sub-subject, which is IEEE 519/2014, which is distortion, which is part of total power factor. We have a new technology to address that very effectively. It makes bidding lower risk, costs more certain, and basically a higher chance of making profit on the project. So with that, it's 8:03. Are there any questions that anybody has at this point? Because I understand it's been a tough and more complicated subject matter than we normally have. If not, 8:03, time to go to work. Thank you very much for attending, and we will address active front-end technologies next week on this class. Have a great week. See you next Monday.
Thanks, Pierce.
Thanks, Pierce.
Thank you.
Thank you.